All right, howdy folks. In this video, what we're going to do is talk about a concept that's really critical to understanding the reactivity of aldehydes and ketones, and that has to do with identifying acidic hydrogen atoms. And by acidic here, we typically mean things that can be removed with hydroxide, and often that means that they'll have a pKa maybe below 25, kind of 30 for sure, definitely have to be below 30. All right, and so we've got 6 molecules drawn here, and I'm just going to ask you to draw out and then label all of the acidic hydrogen atoms. And then for those that are, drawn out, maybe it's a good idea to guess what a pKa would be. All right, and so I'm going to give you a minute to actually do that, which is a very important part of these Professor Carbon videos, is actually to pause them and take a minute or two to actually try to answer the videos before you just listen to me give you the answer. All right, so please pause right now. Okay, popping back in here, what we're going to do is just sketch out some hydrogen atoms. And let me just doodle them on in here then. So acetophenone with this kind of chain dangling off here, the first one, should be on the easier side for these. And the reason for that is because the ketone is aromatic on one side, and so typically that benzene ring really blocks any acidity on the sort of left half of the molecule. There are 2 now here on the alpha carbon that would be acidic, and these are not further conjugated. So yes, there is an extra double bond over here, but if you draw the enolate that you'd get by deprotonating this, there's no way to push those electrons into the double bond or have an additional resonance structure, because there's still 1 additional carbon here that kind of isolates the system via resonance. So that'll do it for that one. This I would estimate to be a regular ketone pKa, and so I would estimate that the pKa here is going to be about 19 to maybe 20. Okay, the next one up here is cyclohexenone, and this molecule is going to have 2 acidic hydrogens, and those would be here. This one is actually acidic because if we draw out that enolate, that anion, we can imagine it delocalizing all the way up top. And so that would give us an additional . Now, even though this is conceivably an acidic spot on this alpha-beta unsaturated ketone, most bases actually preferentially will deprotonate here. So some of our favorite bases like LDA will for sure deprotonate that site of HA, not HB. And so that's particularly important to recognize, is even though HB is acidic, it's not one that typically reacts in most of these reactions. The other common misconception that I encounter with students is that often they will draw an HC, and HC is not one that is acidic. And the reason for that is that if we have that anion, this negative charge is not going to be delocalized into an enolate. And so you can try to draw that enolate, but something really weird should happen if you tried to do that. So we need that carbon in there. And what this is trying to tell you in the structure that does not exist, just going to put an X there, and I'm actually just going to X through this structure too, just to make it super clear that that's not there. But the reason that you don't get that structure is because if we think about that enolate on its side, we have the ketone here and this double bond, and that negative charge needs to be in the sp2 hybridized orbital, not in the p orbitals that are making up the alpha-beta unsaturated system. And so it's an orthogonal orbital, and so it can't be delocalized. And that kind of should make some sense if you actually draw out what it'll look like. You should get kind of nervous with that structure. Okay, overall, I would estimate that the pKa of both of these groups are going to be pretty similar to that other ketone. So the pKa over here, I would call 19 to 20. And this one will be a little bit lower, but not by a whole lot. And so maybe we'll just say 18 to kind of illustrate that. Okay, the next one here is a good one. So this H in the middle here, this HA, And by the way, for all of these that have 2 hydrogens, so both of these have 2 hydrogens, I'm just going to draw one H and assume that you recognize that the other H has the same pKa, especially if the molecule is achiral, they're identical in all ways. All right, so HA here is going to be between not 1, but 2 carbonyls, and so we would call this a beta keto ester. And what that means is that the anion that we would generate by deprotonating between them can delocalize one way, to make one enolate, and it can also delocalize another way if we push that electron density all the way up into the other oxygen. Oops. And so because of that, it's kind of like a double enolate. And so I'm going to estimate its pKa at about 11 because it can be delocalized into both carbonyls. Now, that being said, don't overlook this methyl group. And that methyl group is going to be just like a regular old ketone as well. And so I would estimate its pKa at about 19 to 20. That being said, it's much easier to deprotonate between them than it is on the outside. There are some reaction conditions that will take advantage of both acidic hydrogen atoms and doubly deprotonate the substrate. So that's kind of fun. All right, moving on to the second half here, we've got a couple of additional complicated examples. This one's a trick one. A lot of students might be tempted to put that H in the middle there. As a reminder, this is an acetal functional group, so it's one carbon bound to 2 different oxygen atoms. And it turns out acetals are not very acidic. That's one reason why acetals are commonly used as a protecting group. They're not acidic between those 2 oxygens until you get to really basic things like butyllithium or tert-butyllithium. Then maybe you can do some deprotonating, but definitely not in our standard aldol range. And so this one has none. All right, the aldehyde here is also going to have none. So a bonus trick question, and this one, often students will circle this H, and that one is not counted here. And the reason is very similar to the other answer that we had before for this alpha beta unsaturated ketone up top. The orbitals don't line up the way that you'd expect them to. And so remember, the whole reason that enolates are stabilized is because we want to delocalize that charge onto oxygen as if it were an allyl cation, or sorry, allyl anion. Over here, if you deprotonate that aldehyde, you would have a minus charge, but you can't push that arrow because this oxygen's already got 8 electrons. And so that means that this is an illegal arrow. It would give that oxygen 10 electrons, and we certainly can't do that. And so this one has none. None is the correct answer here. All right, moving on to this Annalynne derivative with an acetate group here. There are actually 2 H's that, or 2 groups of H's that we could encounter here, both of which would have acidic enough pKas. The top pKa here I would estimate as being about 25. And remember, amide functional groups, as well as esters, are less acidic than their ketone or aldehyde components. So remember, the most acidic carbonyl is going to be aldehydes, not at the aldehyde H, but typically at the alpha aldehyde H. So here at the alpha position, the one that we just talked about has no alpha position. So aldehydes are the most acidic at that alpha position, then ketones, then esters, and then amides are way below. And an additional complication with amides is that the NH has about the same pKa. And so I'm just going to put this as about 25 as well. And so that means it's very difficult to selectively deprotonate one of those positions and not the other ones. And so often our standard reactions like alkylating and enolate are problematic on amides because you can accidentally alkylate the NH bond as well. Okay, so that summarizes this video tutorial on pKas. for these alpha positions of ketones. Hopefully you're finding this useful. I'll encourage you to subscribe to our YouTube channel, Professor Carbon, if you're finding these videos useful. You can follow us on Twitter and or Facebook. Additionally, if you'd like to download the PDFs of these videos, you can do so beforehand so that you could actually work through them from that PDF. And we have them all loaded on the Patreon webpage. And so there's a link for that right on our handle on the YouTube channel. So thank you for watching these. Please share them with a friend.